Now, apart from electrifying cars, how else could we improve road transport? Well, let's look at urban transport first. We've seen that the energy usage in the city is dominated by repeated acceleration. So time after time you have to stop and then accelerate and then stop and then accelerate. And each time you accelerate you have to put in half mv squared, and adding them all up, that dominates the energy consumption. So how could you improve things? I mean, there are some obvious things. It's half mv squared, the mass. So if your vehicle is less massive, that saves you energy. Or you put more people in it. It might be the same amount of energy for a car with 4 people, so carpooling rather than 1 or 2, so that gives you better energy use. Reducing speed to half mv squared, so if you only accelerate to 50 kilometers an hour rather than 60, that's going to save you quite a bit of energy. Because it's squared, even a small change in velocity makes quite a big difference in energy. Or you could build different roads, have flyovers or tunnels or something, so you don't need to stop so often. But all of these are problematic. If you make your vehicle less massive, it's probably going to be less safe and less comfortable. I mean, we do have less massive vehicles, they're called motorbikes, but they're generally a major safety risk. People don't seem to like carpooling, it's inconvenient, and people definitely don't like going at lower speeds, and changing roads will be very expensive. There is, however, an easier fix for this, so-called regenerative braking. The basic idea is that, okay, sure, you need to put in energy to accelerate something up, but in a normal internal combustion engine car, when you slow down, that's all wasted by heating up your brake pads. But what if you could store the kinetic energy when you slow down rather than wasting it as heat? Now, there have been buses in the past that have done this using a flywheel. As it slows down, it spins up a flywheel, so the energy is stored in the rotational energy of the flywheel, and then you can connect that to a gear to accelerate you away. But nowadays the more practical way to do it is to use batteries plus the electric vehicle motors. Because the motors in most electric vehicles can operate 2 ways. They can operate the normal way where you put electricity in and get motion out, but they can also work as dynamos where you put motion in and get electricity out. And so a typical electric vehicle, when it's slowing down, you don't use the brakes, you just use the electric motors in reverse, and you're actually recharging the battery as you slow down. So that means that, okay, sure, you speed up using power, then you slow down to a stop, and you get most of that power back, which you can then use for the next time you accelerate the car. Hybrids can also do this. They've got enough battery capacity to be able to store up energy for when you're slowing down. So this is why electric vehicles and hybrids are much more efficient in urban driving. But it makes a little difference at highway speeds when you're not starting and stopping. At highway speeds, when you're driving longer distances, like driving to Melbourne or Sydney, so regenerative braking is not going to help you, the energy use of cars is dominated by air resistance, so drag, for longer trips. So how can you reduce this? Well, we've seen that the drag is a half c aero v squared. So it depends on the drag coefficient, i.e. how streamlined the car is, and also the cross-sectional area. So you can make the car very streamlined. The Tesla Model 3 holds the current record as the most streamlined production car, and you can see people look at it as a white one as a bar, looking like a bar of soap, because it's so slippery as it gets through the air. It's about 30% lower drag coefficient. The other big factor is making the car have the smallest cross-sectional area, and again this is quite a low car, like many race cars, which means a smaller cross-sectional area. But this is a bit unpopular. Nowadays people seem to like to buy SUVs, tall, high cars. It's easier to get in and out, and that means even if it's streamlined, it has a bigger cross-sectional area, so there's going to be more drag. So it helps. A very streamlined low car can maybe gain you 30-40% at highway driving, and this is what some electric vehicles currently do, but it does come at a cost. Another way to reduce energy is to drive slower. Once again, because drag is proportional to v squared, that means going slower makes a big difference. Which is good, but again, people don't generally like to spend twice as long driving somewhere. But if you are in an EV and your battery is getting very low, drop your speed down to 90 kilometers an hour and you'll go much further. could we make things even better still? Well, let's say we wanted something that can go really fast, really well. What would you do? Well, you'd make your car enormously long and thin and put lots of people in it, and very streamlined. You'd also reduce the rolling resistance by, instead of having rubber tyres on a tarmac road, you'd have metal tyres on a metal road. Because your vehicle is so very long and thin, the cross-sectional area covers a lot of people. If you can get, say, 1,000 people in your very long, thin car for a cross-sectional area only slightly bigger than a normal car, that's going to give you much less energy per person per 100 kilometres. And indeed this works. The trouble is they're not called cars, they are called trains. So here's an example. You can see for a bullet train it's extremely streamlined, very, very long and thin. So the cross-sectional area of this is probably 2 or 3 times that of a car, but it can accommodate over 1,000 people. So the energy per person is very low, and it uses electric propulsion. So indeed, as we saw earlier, trains, even high-speed trains, these things can go 3 times as fast as a car and still use dramatically less energy. So that's definitely a way to go. Could we do even better than this? Well, the fundamental limit at these speeds is air resistance, even when it's streamlined. So one possibility would be to run your train through a vacuum tube. And this is the hyperlink concept. The basic idea is you build a long tube, you pump the air out, and then have pressurized vehicles running at very high speeds within it. It's not going to be a complete vacuum inside, so you're actually going to need some sort of suction thing to pull out the air in front and push it out the back, and you're going to get shock waves building inside. The idea also is that these things, rather than using tracks, run with magnetic levitation, so there's no rolling resistance either. And so these could in principle run very energy efficiently at 1,000 kilometers an hour. Whether it's actually economically feasible to build them remains to be seen, but people are investigating it. Another way to avoid air resistance is to go high, because if you're up, say, at 10 kilometers in the atmosphere, the air is 3 times less denser at the surface. So if you have something long and thin and streamlined and put it up at 10 kilometers, that's also going to be more efficient. And we'll talk about flight in greater detail later. So it looks like the way you make a car more efficient. Electrify it is really good in the city and somewhat good in the countryside. Make it low slung and streamlined. But the main way is to make cars more efficient, to turn them into trains or planes.